What is mathematics, really? I mean, is it this rigid, unassailable fortress of absolute truths built on perfect, unwavering proofs? Or is there something, I don't know, far more dynamic, human, maybe even surprising happening behind the scenes? Today, we're taking a deep dive into a really fascinating corner of philosophy. It's called the Maverick tradition in the philosophy of mathematics. We'll be pulling apart sources that honestly challenge our preconceived notions of what math is, how it's done, even what proof truly means, our mission. To extract the most important nuggets of knowledge from these discussions, basically offering you a shortcut to being well informed and maybe, just maybe, having a few genuine aha moments along the way.
Absolutely. And we're going to explore the ideas of Ruben Hersh, who's a real champion of this Maverick approach. He presents his position as a subversive attack on traditional philosophies of mathematics. But we'll also look at the insights and, frankly, some intriguing disagreements from Carlo Cellucci. He's engaged really deeply with Hersh's views, and he offers this robust counter-perspective that helps refine things.
Okay, let's unpack this then. Historically, mainstream philosophy of mathematics was all about foundationalism.
Right. Essentially, research into the bedrock principles of math, the foundations.
But then, around the mid-20th century, a new perspective started to emerge, one that really began to shake things up.
That's where Imre Lakatos comes in. Yeah. He really criticized this mainstream view, said it denied mathematics its true status, having nothing about its growth, especially its creative periods. For Lakatos, the philosophy of mathematics should be about the logic of discovery, not just justifying existing results. He even pointed to the ancient Greek method of analysis and synthesis as an early example of this more dynamic approach.
So it's not just about what math is, but a whole reevaluation of its process, how it develops, highlighting that dynamic nature Lakatos talked about. But for a discipline that seems so, well, immutable, how radical was that idea back then? Did people push back immediately?
Oh, profoundly radical. A huge challenge to the prevailing thinking. And Ruben Hersh is just central in carrying this Maverick tradition forward. One commentator even called him the mother of all gadflies for his, persistent questioning. He champions this humanist view, stressing that mathematics is human. It's part and fits into human culture. That's a direct counter to the old idea of some abstract, timeless, objective reality.
Okay, but if mathematics is a human activity, what is mathematics then? Seems simple, but when you dig into it.
Oh yeah, the common naive answer, mathematics is what mathematicians do. That just goes in circles, doesn't it? Hersh offered a partial answer. He said, mathematics is the subject where statements are capable in principle of being proved or disproved, and where proof or disproof bring unanimous agreement by all qualified experts.
That sounds pretty definitive, at first blush. Unanimous agreement implies certainty.
It does, yeah, but there are crucial qualifications.
Yeah.
Things that quickly undermine that feeling. Cellucci points out that proof might not be deductive proof in the way we usually think. It might be something else, something more nuanced we'll get into. And critically, empirical research actually shows there is not universal agreement among mathematicians regarding what constitutes a valid proof. It's just not there. Morris Klein even provocatively states, the proofs of one generation are fallacies of the next.
Wow.
Yeah. So it raises this huge question. If even the experts don't always agree, what does that really mean for mathematical certainty?
So the immediate takeaway seems to be that mathematical truth isn't some fixed bedrock. It's more like a social construct. It evolves.
Exactly. Subject to human consensus and evolution. It's a living thing.
Okay. So for many of us, philosophy of mathematics feels, I don't know, really specialized, almost isolated maybe, far from daily life. But these sources are saying that wasn't always the case.
Not at all. That's absolutely right. I mean, from Plato all the way to Kant, philosophy of mathematics was just treated as part of a general approach to human knowledge. It was only really the end of the 19th century with people like Frege that it became this super specialized subject. And Hersh argues this led to it becoming, in his words, encapsulated, isolated, timeless, ahistorical, inhuman.
Right. It completely lost that connection.
Yeah, lost connection to the human mind, to science, to society, just in its own world.
Yeah, so if it wasn't always so isolated, how did math originally arise as part of human knowledge?
Well, like almost all knowledge, really. It originally arose from very practical needs, dealing with the external world, geometry, for example, the Egyptians needing to remeasure land after the Nile floods every year. That's practical. Arithmetic came from Phoenician trade. Calculus, well, from the need to understand planetary motion. Physics, basically. As Poincaré noted, the desire to understand nature has had on the development of mathematics the most constant and happiest influence. He even had that great line about a pure mathematician who should forget the existence of the exterior world. He'd be like a painter without models. His creative power would just fizzle out.
That's a fantastic analogy, like a painter needing real subjects. But, okay, if we want to understand the nature of math, should we just ask mathematicians? I mean, they're the ones doing it, right?
Well, Hersh does sort of suggest that the philosophy of mathematics is the working philosophy of the professional mathematician. But trying to nail down a single working philosophy, that's like herding cats. Brilliant, complex, often contradictory cats. It just varies wildly, period to period, school to school, even mathematician to mathematician.
Can you give us an example? Just how different can these working philosophies be?
Oh, sure. Take David Hilbert.
Yeah.
He emphasized absolute logical deduction, rigor above everything else. And you have someone like the Italian mathematician Federico Enriquez, who famously said, "We aristocrats do not need proofs. Proofs are for you commoners."
Wow, really?
Yeah, indicating this reliance on intuition, on just seeing the truth, not formal deduction. Very different approaches.
So relying only on mathematicians' working philosophies, that might just turn the philosophy of math into history, maybe, not a deeper look at its nature.
Exactly. And the history of math itself is often written based on the finished form, you know, the polished result, which has very little to do with the messy, real process of discovery. As Lasserre, the historian of science, put it, asking a working mathematician, "What is mathematics?" might just get you a reply like, "I don't know."
Huh.
Yeah, but it doesn't stop them doing math. Reflecting on the nature of math, that's a whole different skill set. It's separate from just calculating or proving.
Okay, this distinction between finished form and the real process, that brings us to this crucial idea you mentioned, the front and back of mathematics. This feels like it's going to crack open a lot of assumptions.
It really does. Hersh adapts these terms from the sociologist Irving Goffman. The front of mathematics is what you see. Classrooms, textbooks, journals. It's the polished, published, established mathematics. The back is where the actual creative work happens, among working mathematicians in formal settings, behind closed doors. And the crucial point is that the performance scene up front is created or concocted behind the scenes in back. And mainstream philosophy, Hersh argues, just completely ignores this back.
So it's exactly like a theatrical production, right? You see the polished show on stage.
Right.
But the raw, groundbreaking work, the innovation, that happens backstage, away from view. And the really radical insight here seems to be, if you ignore the backstage, you just fundamentally misunderstand the entire performance of mathematics itself.
Precisely. It's reorienting where the real magic happens. And Cellucci refines this even further. He argues the back isn't just like preliminary scribbles or incomplete versions of the finished math. It was the creative work of the mathematician, primarily the discovery work. But they both agree. It's impossible to understand the front while ignoring the back.
Yeah.
When mainstream philosophy only looks at the front, it just misses the dynamic process, how math is actually made.
Okay, so proof. It's absolutely central to mathematics, seen as its backbone. Mainstream philosophy bases proof on this finished form, this front of math. What does that mean for how we understand proof itself?
Well, interestingly, Hersh also focuses on proof as the front side of mathematics. It's a bit surprising, maybe. For him, deductive proof is the standard for acceptance of one's findings into the body of established mathematics.
Yeah.
It's deduction from established mathematics. That's key for him. Now, he acknowledges that plausible reasoning, like induction or analogy, is essential in finding the deductive proof.
Right, the creative bit.
Yeah, the discovery part. But he maintains it's just a heuristic tool, a preliminary step. It's not part of the proof itself. Only deduction, he argues, legitimates a result as established.
Okay. But given everything we've discussed about the human element, Hersh takes this incredibly bold step next, doesn't he? Challenging our deepest assumptions about math, its connection to truth and certainty. What exactly does he argue?
Oh, it's a truly provocative claim. He argues that mathematics cannot be said to be about truth.
Wow.
Yeah, because mathematicians' proof does not guarantee truth. And it's not about certainty either, because mathematics is human, and nothing human can be absolutely certain. And Cellucci completely agrees on this point. He brings in Gödel's second incompleteness theorem.
Gödel, right.
Which famously showed that no sufficiently complex formal system can prove its own consistency, meaning it's impossible to prove the consistency of strong mathematical systems by absolutely reliable means. They even suggest the very concepts of truth and certainty didn't really arise from math or science anyway. They came from religion.
That really does shake up the common view. So the core nugget is Mathematical certainty, as we usually think of it, it's basically an illusion.
That's the provocative takeaway, yes. An illusion.
Okay, wow. So Hersh takes a kind of machete to the idea of absolute truth in math. But if his view deductive proof as the only real proof doesn't guarantee truth or certainty, and it kicks out plausible reasoning, where does Cellucci see the critical flaws in Hersh's own view of proof?
Right. Cellucci points out three really serious problems with limiting proof just to deduction from established math. First, he says, it just can't prove propositions that aren't deducible from what's already established.
Like completely new ideas.
Exactly. Think of George Cantor's work on different sizes of infinity, revolutionary stuff. His ideas were fiercely opposed by the establishment, people like Kronecker, Hermite, because they went way beyond what was accepted then. So if only deductive proof from established math counts, how could revolutionary ideas like Cantor's ever get proved?
Good point. Okay, what's the second problem?
Second, it implies mathematicians are completely replaceable by computers.
Ah.
If proof is just deduction, well, an algorithm could just list all possible deductions. Alan Turing himself considered this, even if it's, time-consuming. Timothy Gowers even suggested computers could eventually supplant us completely. But then you have Gödel's first incompleteness theorem, which suggests there will always be true mathematical statements you can't prove within a given system. Cellucci argues this implies it will never be possible to replace the mathematician by a machine. So what's the unique human role if it's not just deduction?
Right, that leaves a gap. And the third problem?
Third, it suggests all mathematical knowledge is ultimately contained in really elementary propositions like 1 plus 1, 2.
How does that follow?
Well, if deductive rules are non-ampliative, and this is key, it means the conclusion is already contained in the premises. You're just unpacking what's already there.
Like getting things out of a box that were already inside.
Exactly. So if you trace all knowledge back deductively, you end up at these very basic, maybe innate capacities. Cellucci just calls this quite implausible. Doesn't feel right.
Okay, so deductive proof, as Hersh frames it, seems to have these pretty deep flaws according to Cellucci. What's the alternative Cellucci is putting forward?
Cellucci proposes analytic proof as the true mathematician's proof. And this idea goes way back, ancient Greece again. A key example is Hippocrates of Chios, squaring those crescent shapes, the lunules. Instead of starting with axioms, Hippocrates worked sort of backwards. He non-deductively arrived at hypotheses like similar segments of circle have the same ratios as the squares on their bases.
Yeah.
These hypotheses were sufficient conditions to solve the problem, and they were considered plausible based on what was known then.
So analytic proof is like working backward from the problem to find plausible starting points or hypotheses.
Like
detective work, yeah.
Exactly. Like detective work. It involves both an upward path from the problem to plausible hypotheses that are sufficient to solve it, and a downward path from those hypotheses back to the problem, showing how it gets solved. So it's a means of both discovery and justification at the same time. And crucially, analytic proof can use hypotheses that cannot be deduced from established mathematics.
Because the rules are different.
Because the rules for generating hypotheses are ampliative. They expand our knowledge. They can generate genuinely new ideas and insights. They bring new information into the picture that wasn't strictly derivable from what we started with.
So it's like finding something entirely new outside the box, prompted by the problem itself, rather than just unpacking the box.
That's a great way to put it, yes.
And this analytic view, it neatly solves those three problems with Hersh's deductive view you mentioned.
It absolutely does, according to Cellucci. If analytic proof is the real mathematician's proof, one, it is possible to prove propositions not deducible from established math because it allows these ampliative plausible hypotheses. Two, mathematicians cannot be completely replaced by computers. Why? Because there's no algorithm for producing novel, plausible hypotheses that might create entirely new ways of thinking. It highlights that human creativity.
Right, the leap.
The leap, exactly. And three, not all mathematical knowledge is ultimately deduced from elementary propositions because analytic proof uses ampliative rules. It allows for genuine expansion of knowledge.
Okay, but Hersh objects to this, doesn't he? He calls these things arrived at by plausible reasoning just unproved conjectures. How does Cellucci handle that pushback?
Cellucci refutes that directly. He explains that analytic proof doesn't justify the hypotheses by the rules of discovery themselves. That's not the point. It justifies them by their plausibility. And that plausibility is established through a rigorous process. He calls it a plausibility test procedure. which
Yeah.
involves deducing conclusions from the hypothesis, checking for contradictions, comparing it with existing knowledge, seeing if it fits. So analytic proof establishes results as plausible, just like deductive proof establishes them as, say, warrantedly assertable. Neither one is claiming absolute truth or certainty.
Ah, okay. So the key takeaway here is that both types of proof offer a kind of justification, but maybe their goals and methods are different, moving beyond just true-false.
Exactly. They're different tools for different or maybe overlapping jobs. It's not a simple binary.
This split between deductive and analytic proof feels really significant. How does it change our understanding of different kinds of mathematics? Not just how it's proved, but the math itself.
Well, it leads Cellucci to make a distinction between what he calls normal mathematics and revolutionary mathematics.
Okay.
Normal mathematics, the kind most mathematicians do most of the time. It doesn't usually require hypotheses outside what's already established. Puzzle solving within a known framework. Revolutionary mathematics, though, involves introducing hypotheses that cannot be deduced from established math. It ties together previously separate areas or opens up entirely new fields.
Like those big turning points in math history, paradigm shifts.
Exactly those. So deductive proof is adequate for normal math, mostly.
Yeah.
But it's clearly inadequate for revolutionary math. Analytic proof, on the other hand, Cellucci argues, is adequate for both. It handles the day-to-day and the breakthroughs.
That really shifts how we might see mathematical progress then. It's not just incremental steps within a fixed system. And this connects to something called the inexhaustibility of mathematics, right?
Yes, exactly. Gödel, again relying on axiomatic proof, saw this inexhaustibility kind of negatively, like a limitation. No single system of axioms can capture all true mathematical propositions.
A bit depressing, maybe.
Yeah, a bit. But if we embrace analytic proof as the real mathematician's proof, we can interpret this inexhaustibility positively, as a feature, not a bug.
Okay, what does that positive interpretation look like for us? How does it feel different?
It means mathematical knowledge becomes this infinite problem-solving process, where beyond every hypothesis, one looks for deeper hypotheses. Each new, deeper hypothesis makes you see the original problem with new eyes, as Proust put beautifully. It leads to this unlimited deepening of the problem, suggesting just endless frontiers for discovery, not some limited set of truths we're trying to find.
So the profound shift is from thinking of math as a finite body of knowledge to uncover, to seeing it as an infinite journey of discovery.
Precisely. An ongoing, potentially endless, creative process.
Okay, so proof isn't just about convincing someone something's true, or even about certainty anymore. It's more about explanation, understanding.
Well, Hersh thought proof in research was mainly to convince, while in the classroom it was to explain. But many mathematicians, like Gleason, actually contend that proofs really aren't there to convince you that something is true. They're there to show why it is true.
Ah, the why.
The why. And analytic proof, Cellucci argues, explains because its solution is built on hypotheses that are strictly connected to the problem itself. They reveal essential aspects. It's about insight, not just ticking a proven box.
This reevaluation of proof, moving from certainty to understanding it, must also shed light on things that got sidelined, right? Like diagrams and proofs. They feel so intuitive, so helpful for discovery, but where do they fit?
They fit perfectly in the analytic view. I mean, go back to ancient Greece. Diagrams were essential. Remember Aristippus? Shipwrecked?
Vaguely.
He saw geometrical figures traced in the sand and was reassured, knowing he'd landed among Greeks, not barbarians. Diagrams signal civilization, mathematical thinking. Yet, fast forward to the 20th century, and diagrams were often seen as non-rigorous, even misleading, informal proofs.
Right, you had to write it all out symbolically.
Exactly. But as Hersh notes, a proof can be words, or words and diagrams, or even diagrams only. And analytic proof totally justifies their use, because hypotheses can be derived from the data you acquire from the diagram. They become integral to the discovery and justification process.
Can you give us a quick example just to make the diagram's role in analytic proof concrete?
Sure, absolutely. Think about the Pythagorean theorem. Instead of a formal deductive proof with just symbols, imagine a visual demonstration, like the dissection method, where you cut up squares and rearrange the shapes to show a back plus b orc c sine equal 1. To prove that analytically, you might look at the diagram and non-deductively hypothesize, say, that the sum of the angles of a right triangle is equal to 2 right angles.
Okay, that seems plausible, and maybe you need it to make the rearrangement work visually.
Right. It's plausible, and it's sufficient to complete that diagrammatic proof. Then you might go deeper and hypothesize that a right triangle is half a rectangle to justify that first hypothesis. This process seeking deeper, plausible hypotheses, often prompted by visual insight from a diagram that's characteristic of analytic proof. It's about seeing relationships, not just deriving symbols.
Okay, fascinating. Finally, let's touch on the nature of mathematical objects themselves. Numbers, shapes, sets. If mathematics is human, as Hersh insists, and it's not about absolute truths, do these mathematical objects actually exist out there in some detached Platonic realm?
Yeah, that's the big question. Mainstream views often lean towards mathematical Platonism. These objects exist independently, timelessly, and we access them through intuition. But Cellucci offers a different reading, even of Plato himself, suggesting that maybe mathematicians, while alive, can't contemplate this non-physical reality directly. Instead, they introduce mathematical objects as hypotheses specifically to solve problems.
So they're tools we invent or posit.
Sort of. These objects exist only in the minds of the mathematicians who hypothesize them, and in the minds of the people who make use of them. They are real in that sense. Hersh agrees with this kind of view, calling their reality mental cultural.
Mental cultural, I like that.
Yeah, so numbers and shapes are maybe less like discovering continents that were always there, and more like inventing tools or concepts that arise from and then shape our problem-solving efforts.
Wow. So this whole deep dive, it really reveals a profound shift in thinking about mathematics, doesn't it? It moves us from seeing math as this rigid, certain, finished thing to something dynamic, human, constantly evolving, a process. It sounds like it's much more about plausibility than absolute truth and focuses on the ongoing creative work of discovery, not just presenting the final result. It feels, well, kind of liberating, actually.
It is, and despite the storming attacks from mainstream philosophers over the years and people prematurely declaring it a failure, the Maverick tradition, particularly through Hersh's work, has really succeeded in reconnecting the philosophy of mathematics to the bigger questions about human knowledge. It reminds me of that cynical observation by Max Planck, the physicist.
Oh, yeah.
He said something like, "A new scientific truth does not triumph by convincing its opponents, but rather because its opponents eventually die, and a new generation grows up that is familiar with it."
Ouch. But maybe true?
Maybe. And the Maverick tradition, well, it seems to have arrived as a legitimate theme of philosophical investigation. It's challenging us to rethink the very foundations.
Yeah. And this idea of mathematics as an infinite problem-solving process, always seeking deeper hypotheses, new ways of seeing, that feels incredibly powerful. It makes you wonder, what if we applied this analytic proof mindset, this way of thinking, to other areas of our lives? What if, instead of always chasing absolute certainty or focusing only on the finished product, the final conclusion, what if we embrace the ongoing process, discovering plausible hypotheses, seeking deeper explanations? How might rethinking proof in that broader sense in other areas of life actually change our approach to understanding things, maybe even to innovation? Definitely something to mull over until our next deep dive.